We're going to have a brief respite from hypothesis testing and confidence intervals and the distribution of the samples, and just talk about a kind of different thing called linear regression. Before, we were really mainly concerned with graphs where the vertical axis was frequency, and now the graphs that we're going to be drawing are going to have numerical variables on both axes. So you collect a lot of data, and those data points have two values, for one value for variable number 1 and one value for variable number 2. And if you plot those variables on a graph, then we call it a scatter plot because the dots are kind of scattered around. And you'll observe that in this first graph, I kind of missed. In the first picture, I can draw a line down the middle of this graph, and it looks like the general trend of those dots that I drew kind of follows that line. Sometimes you call it a trend line. Sometimes you call it a line of best fit. It's not going to work in this second picture. It kind of makes a letter U shape, so I'm going to do my best to kind of fit a parabola to this graph. So the theory I'm about to teach you does apply to scatterplot number 1, but does not apply to scatterplot number 2. There's lots of other kinds of regression if you have a nonlinear trend in your graph, but it's just not part of this class. Okay, so if the general trend of the dots is kind of increasing as you read left to right, then those are going to have a positive association between the variables. And if the trend is generally decreasing, then there's going to be a negative association in the variables. These are statements about the slope. In the first plot, all of the dots are kind of grouped together in a pretty small range, so there is a small amount of scatter. And in the second picture, the dots are kind of grouped a little bit wider apart, so there's more scatter. Okay, so let's imagine that we were trying to predict where the next dot would go. So I'm going to add another dot to the first graph, and let's see if you can predict where it will go. Is it reasonable? Does this dot over here, does that look like it's following the trend line? No, obviously not. In the first picture, because all of the dots are kind of grouped together in a line, it's really easy. Oh, that is a reasonable place for the next dot to go. But in the second graph, because the dots have more scatter, there's a lot of different places that I could put the dots, and it's still believable that that could be another dot in the data set. So the idea here is that when there's a small amount of scatter, it's easier for us to make predictions about where the next dot would go. And when there's a large amount of scatter, then it's more difficult. Our predictions are going to be less accurate. So when there's a small amount of scatter, we call the scatter plot strong. And when there's a large amount of scatter, we call it weak. If you can't identify a trend at all, if the dots are just all over the place, this is like the weakest possible association. So we say that there's no association. The correlation coefficient measures how strong the correlation is. It's always a number between -1 and +1. And +1 is the strongest possible positive correlation, and -1 is the strongest possible negative correlation. So just looking at the pictures that I've drawn before, this small amount of scatter, to me, this maybe looks like something like R equals, maybe we would get 0.98, so 98% correlated. This one is a little bit weaker, so we're going to have a slightly smaller value for R. And this one, maybe R could be 0.85. And then this one here where there's just no association at all, it's just completely random where the dots are, this one is going to be R equals 0. And then just for the sake of completeness, if the dots line up in a perfectly straight line, then that's where you're going to have a perfect correlation. In this picture right here, since the slope of this is decreasing as I read left to right, this would be an example of R equals -1, a perfect negative correlation. We make choices for the variables. We're going to use the input variable, the variable on the x-axis, as the predictor variable, and then we're going to put the variable on the y-axis that we think is going to respond to changes in the predictor. So let's suppose we had data on the number of hours that students were spending on homework. I don't know if you guys know this, but my math lab actually does tell me this number. And also, obviously, I have data on students' grades on test 1. So I'm just going to make up some numbers, and we're going to use our calculator to find the correlation coefficient. So my choice in this problem was to use the hours spent on the homework as the predictor and the test score as the response. The first step is to put the data in the calculator. It's important that you always make sure to put the predictor variable in as L1 and the response variable in as L2. Then what we're going to do is push the stats button, and then over in the calc tab, there's actually 2 choices for our answer. We can either choose option number 4 or option number 8. And my experience has been it's the same piece of information. It's just they just change the order that the numbers come in. And option 8 oftentimes matches the order that my math lab wants it in. I always forget to do this. It doesn't give us an R value because we have to turn that feature on, and I always forget to do it. So let's do it now. What you need to do is open the catalog. So if you push second 0, that will bring up all of the possible things. And what you're looking for is something that's called diagnostics. So you have to go all the way down. There it is. You have to go all the way down until you find diagnostics on. You push enter once to select the command, diagnostics on, and then you push enter again to execute the command. So now my diagnostics are on. I don't know why anyone would ever want their diagnostics off. Push the stats button and you go to calc, and then we're going to go down to option 8, linreg A plus bx. And now that our diagnostics are on, it is going to spit out an R value. So we ended up with a very strong positive correlation. In this example, R equals 0.962. So the takeaway from this example is, according to our data, change to a different student, and that student has an increased number of hours spent on the homework, then we would predict that they would also have an increased test score. If we got a negative correlation, that's crazy in this context, but what that would mean is the more hours you spend on homework, the worse your test score is. So I just want to introduce this idea of causality, or cause and effect. And think about it in the context of this problem. Our variables are the time that you spend on the homework and your test score. So when we're looking at these, I think that really intuitively there should be some kind of a cause and effect here, right? I mean, if you spend more hours on your homework, then that means you were probably better prepared for the test, and so then you ended up with a better test score. So I just want that idea to be in your head as we go through these things, because there's going to be an important takeaway at the end about the relationship between correlation and these ideas, cause and effect. He's supposed to be thinking? Does it look like he's just poking himself in the face? Okay, so let's talk about the other piece of information that the calculator spits out in this process. It's called the line of best fit, and you'll also see it called the regression equation. Here's this familiar form from college algebra. I know people a lot of times put mx plus b, but just to make our answers match with my math lab, we're going to do b plus mx. I hope you can keep up. Anyways, just to remind you what the interpretation of these letters is, m represents the rate of change, so this is something like miles per hour, and then the b is the y value that you would get. You can see if I plugged x equals 0 into this equation, then that whole piece would go away and I would just be left with b. Okay, so I'm going to do an example where the data is already preloaded in StatCrunch. The context of this problem is about predicting the price of a train ticket based on how far apart the cities are. So in this problem, we have to try to decide which one is going to be the predictor and which one is going to be the response. Just because they give them to you in the order where one of them is first and one of them is second doesn't mean they're always giving you the predictor first. In this problem, I think that we would use the distance between the cities to predict the price of the ticket. Okay, so we're going to open the data in StatCrunch, and then they want us to make a graph. We want to make a scatterplot. Then the x variable, this is the predictor variable, I'm going to use the distance to predict the price. Okay, looks like we have a lot of different things you can change here if you want to label the axes or something to make your graph look pretty. I'm just going to try this with compute. Okay, and we get this graph. Let's see if that matches with any of the graphs in the picture. So it's definitely a positive trend, so I'm ruling out A and D because they're both negative. I'm also ruling out C because this correlation is too strong. The actual correlation is a little bit weak. It looks like there are some close cities that it's very expensive to take train rides through, and then this is kind of a far city. The cities are far apart, and it's kind of cheap, so I'm choosing B. Okay, so to me it looks like this graph is linear and strong and is basically increasing at a constant rate. Nice work. I kept clicking the things wrong. I almost ran out of tries. Have you guys noticed that my math lab was a little bit annoying? I don't know if you noticed that, but okay, now the next thing it wants us to do is to compute R, the correlation coefficient, and also to write the equation of the regression line. So in stats, there is a regression option, and we're going to choose simple linear regression. The predictor variable is going to be distance, and the response variable is going to be price. Then there is a lot of other options. I'm just going to leave these all set on default. All we really care about is just choosing the x variable and the y variable. And then it gives it to us right here. The ticket price right here is a relationship between the distance in miles and then the price of the ticket. So this distance in miles is the x variable and the price of the ticket is the y variable. It also gives us this correlation coefficient right here, 0.7956. What do they want? Round to 3 decimal places. So 0.796. Round to 1 decimal places. The predicted ticket price is 65. Round to 1 decimal places. That doesn't make sense. This is an amount of money, but whatever. Round the coefficient to 4. Round the constant to 1 decimal place. Round the coefficient to 4 decimal places. Cut me some slack, buddy. All right, so this should be 0.1970. Okay, let's take a minute to talk about the interpretation of slope. So the way that I understand this, I memorized this formula based on something that is a simple example to me. 30 miles per hour is also a rate of change. So let's just interpret that. And then what we'll do is we'll just copy and paste the variables from our problem into the interpretation of 30 miles per hour. So what does it mean to be driving 30 miles an hour? That means for every 1 hour that you drive, the amount of distance that you've traveled increases by 30 miles. So in this problem, hours are the predictor variable, and distance, this is the response variable. So this is the form of the way that you explain the rate of change. So let's just copy and paste our understanding of slope into a general understanding. So I'm trying to make a statement like, for every one predictor variable, the response will increase by the slope. Okay, for every one predictor variable, in this problem the predictor was distance, so for each additional mile, so far I'm leaning towards answer B, for each additional mile, because the predictors in this problem are distance, is associated with an increase of blank in the average price. So this right here needs to be the slope, so is associated with an increase of $0.197 in the average price of the ticket. Good job. Okay, now they're asking me to interpret the y-intercept here. So the y-intercept is supposed to be the value when x is 0. So that's supposed to be, the y-intercept is supposed to be the y value. In this problem, that's the price, when the x variable is equal to 0. In this problem, the x variable is distance. So we're trying to interpret how much should you have to pay for a train ticket when the distance between the cities is 0? Okay, so this is nonsense. It doesn't make sense. No one would take a train between two cities that are 0 miles apart. I don't even know how two different cities can be 0 miles apart. So in this problem, the y-intercept doesn't make sense, and that's common. You know, the slope always makes sense, but sometimes the y-intercept makes sense and sometimes it doesn't. So in this problem, that's just garbage. It doesn't help us. All right, one last part of this. Use the regression equation to predict the cost of a train ticket from Boston to New York. That's a distance of 196 miles. Okay, so I'm going to just jump back and look at the regression equation that we got, and they're asking us to predict the ticket price, and then they're giving us the distance. The distance that they gave us was 196 miles, so all I need to do is just plug that into the equation, and I got $104.31. So you need to be very careful with linear regression. It can feel like a much more powerful tool than it really is. The first mistake that you can make when you're using linear regression is to try to make predictions that are far away from the data that you have. Okay, so I've drawn a little scatter plot here of the year, what year it was, and what the Olympic record was in that year. If I draw the line of best fit to this equation, then it ends up down here. And if I make predictions, let's say this is the year, like the year 3000 or something, then if I were to make predictions in the year 3000 based on the data that we have right now, I would actually predict a negative 40-yard dash time. So this means that the racer, they finished the race before it even started. And I don't care how fast you are, that's not possible. So you know, you can only use linear regression to make predictions around the data that you have. It is very tempting to say that because variables are correlated, that means that there must be some kind of cause and effect. One of the big things that you're supposed to take away from Stats 1 is that this is not true. People do it all the time. It drives me crazy. It should drive everyone crazy. It's just junk. Just because things are correlated does not mean that there is a causal relationship between them. This is just a fact, okay? There is a strong positive correlation between ice cream consumption and death by drowning. True fact. What this means is the more ice cream that a city consumes, the higher the rate of drowning is. So the fallacy would be to imply cause and effect, would be to say that eating ice cream is what causes you to drown. Is that crazy? Should we ban ice cream now? I'm just trying to stop people from drowning. Should we ban ice cream? Oh, ice cream does not cause drowning. In this problem, there is a lurking variable. The lurking variable is the time of year, okay? People eat ice cream in the summer and people go swimming in the summer. So both of those things just naturally happen at the same time, but there's no causal relationship at all. All I can say is you're more likely to eat ice cream in the summer and you're more likely to go swimming in the summer. But those two things, like one isn't causing the other one. Actually, summer is what's going on. In fact, there doesn't even have to be an easily identifiable lurking variable. There's correlations that are just happening all the time. Just any time that two variables change at the same time, that you can always find a correlation between them, even if they have absolutely nothing to do with each other. So I want to draw your attention to this kind of silly website called Spurious Correlations, where they have a bunch of data sets and they just wrote a computer program that just trolls through these data sets and finds all these correlations. So here's suicide by hanging and U.S. spending on science. Okay, I like this. The number of people that drown by falling in a pool has a correlation with the number of Nicolas Cage films. So, the fallacy here would be to believe that Nicolas Cage appearing in a movie is causing people to drown by falling in a pool. And those things could not be farther apart from each other. They have nothing to do with each other. They just both coincidentally happened at the same time. There isn't even a lurking variable. You should go to this website and just scroll through these. There's a bunch of funny ones about cheese consumption and people dying by being tangled in their bed sheets, Miss America and doctorates in engineering and all kinds of funny things. So check it out if you've got a free minute. So I want to arm you with this new idea. And anytime somebody tries to spin statistics in order to trick you by bringing up the fact that things are correlated and trying to somehow imply that there's a cause and effect relationship with them, boom, you can just out with this right away. Correlation does not imply causation. Okay, so kind of a light lesson this week. I need to jump in and get back to grading everybody's tests. So, please hop in and try that, my math lab homework, and reach out to me if you get stuck on anything. Thank you, everybody.